In this video, we'll talk about Gibbs free energy, G, and its relation to entropy, how to calculate entropy for chemical reactions, standard molar entropies, and the free energy for chemical reactions. Okay, so the free energy is going to determine the spontaneity of a process at a given temperature. So free energy, just like enthalpy and entropy, is a state function, so it doesn't matter how we get there. And the definition of free energy is going to be equal to the enthalpy minus the temperature times the entropy. And if we're going to restrict this to looking at just one single temperature, we can rewrite this equation as delta G equals delta H minus T delta S. Okay, so how does delta G tell us about spontaneity? Well, delta G is related to the delta S of the universe. Specifically, the delta S of the universe is equal to negative delta G of the system divided by the temperature when temperature and pressure are constant. The details of this are in the textbook, but one way to think about this is if you made this look like the delta S of the universe, then it would be dividing everything else by minus T. You'll notice these will cancel out, and so we're left with the enthalpy of the system divided by the temperature is the entropy of the system. And we know that this right here, when we talked about how the delta S of the surroundings is related to the heat, that's where this equation comes from. So we get a clever way of making the delta S of the system and the delta H of the system relate to a value that we'll call delta G, and this applies to just the system. So because we have this relationship between the delta S of the universe and delta G, we can see what delta G means for spontaneity. So since they're directly related to each other but have a negative sign, the sign for delta G for a spontaneous process is going to be opposite of delta S. So if delta G is negative, that means the delta S of the universe would be positive, and that would be a spontaneous process. Likewise, if delta G of the system is greater than 0, the delta S of the universe would be negative, and the process would be not spontaneous. And if it was equal to 0, we have a process at equilibrium. So why do we bother using delta G instead of delta S of the universe? And this goes to this idea right here. Can we actually measure the entropy of the whole universe? Certainly not. But what we can do is measure everything that's related to just our system. And this way, we can find the delta G of just our system, and we know that we can get the delta H of our system and the delta S of our system, and hence we can see something that relates to the delta S of the universe just by looking at our system and get a spontaneity condition using things that we can actually measure in the lab. So let's look at this in practice. Let's consider the vaporization of benzene. So we have the heat of vaporization and the entropy of vaporization, and we want to know, will benzene boil at 60 degrees Celsius and 1 atmosphere? Well, we can do this by looking at our equation. So delta G equals delta H minus T delta S. We plug in our values. And a few things to watch out for. First of all, we'll put the temperature in Kelvin. We always need to convert to Kelvin when we're doing these thermodynamics problems. And you'll also notice that the units for entropy are usually in joules, whereas enthalpy are usually in kilojoules. And so we have to convert one of them. And if we plug all of this in, we get a delta G is equal to 1.77 kilojoules per mole. So this is a positive value. So this is non-spontaneous. And so the answer to this question, does it boil at 60 degrees Celsius, is no. No, it does not. So with this in mind, let's think about this question. So under which circumstances is a process going to be spontaneous at all temperatures? So here we have a list with delta H being positive or negative and the delta S being positive or negative. Okay, and the answer to this is C. So to be spontaneous at all temperatures, delta G has to be negative. And for this to happen, delta H would have to be negative. And for this whole term to be negative, since temperature is negative, delta S has to be positive for this whole term to be negative. So if delta H is negative, delta S is positive, delta G will always be negative, and always be spontaneous. So again, we can see this for the delta H term to be negative, delta H has to be less than 0, and for this whole term together to have to be negative, delta S has to be positive on its own. We can extend this to looking at spontaneous conditions for all of the following. So if delta H is negative and delta S is positive, and these other conditions, so this one will be spontaneous at all temperatures because delta G will always be negative. If we look at this one here, if delta H is positive and delta H is negative, negative T delta S will also be positive, and so delta G will always be positive. And so this one will never be spontaneous. These two are a little trickier, and this has to do because of the relationship with temperature to this T delta S term. So if delta H is positive and delta S is positive, T delta S is a negative term. So if we increase temperature, the negative will be bigger. And so this will be spontaneous at high temperatures. Likewise, if delta H is negative and delta S is negative, negative T delta S is a positive value. So if this temperature is very high, the second term is a bigger positive and it won't be spontaneous. So these are only spontaneous at low temperatures when this T delta S term is relatively small. Next, we'll talk about some quick qualitative ways to predict the sign of delta S for reactions so that we can make judgments like we did for spontaneity based on just the sign. So some general rules: the entropy is going to increase when the moles of gas increase. So if we look at this system, we can see we have 0 moles of gas going to 2 moles of gas, so we expect the delta S to increase. For the second system, we have 2 moles of gas going to 1 mole of gas. For these solids, we won't worry about it, so the entropy will decrease. And for this system, we have 2 moles of gas on this side and 2 moles of gas on the other side, so we don't really have a way to predict based on the phases alone for this third reaction. We can calculate delta S if we don't see the moles of gas changing, similar to the way that would calculate the enthalpy for a reaction. So just like House's law with delta H, the delta S for a reaction is going to be equal to the sum of the delta S for all the products minus the delta S for all the reactants times their stoichiometric coefficients. So if we look at this reaction as an example, given these standard molar entropies, we could do the products, so that's 2 times the HCl, minus the reactants, so that's 1 H2 and 1 Cl2, giving us this answer: the entropy of the reaction is slightly positive at 20 joules per Kelvin. Let's do another prediction. Which of these following molecules will have the highest entropy at 25 degrees Celsius? And the answer for this one is D. This gives us one more property for predicting entropy that we'll look at, and that has to do with the degrees of freedom within a molecule. So for this question, we know that the gases are going to have more entropy than the solids, so it's definitely not one of those two. And then if we look at these three, so H2 looks like this, water has a shape like this, and the C3H8 might look something like this. And if these are all gases, they're all going to have the freedom of movement of a gas particle, but you can see this compound here also has more degrees of freedom because it can shift around all of these bonds and wiggle around in a lot of different ways. So when we get to gases, not only is gas phase higher in entropy than any of the other phases, but gases with larger molecules with more bonds that can move around are going to have a higher entropy than the smaller gas molecules. And here's just a table showing some examples of how, as the complexity increases, the entropy also increases. Let's look at another example here, seeing what has higher entropy: a mole of helium at 25 degrees Celsius or a mole of helium at 100 degrees Celsius. It stands to reason that at a higher temperature there's more movement, so it'll be the helium at a higher temperature that has a higher entropy. Now we can look at calculating the entropy for helium at this higher temperature given the entropy at the lower temperature. To do this, we can look at this transformation. So we're going from helium at 25 degrees C or 298 Kelvin to helium at 373 Kelvin. And so we can use this equation. The delta S is equal to NCP ln final over initial. since this is a constant pressure process. And this is going to be equal to 1 times our standard CP for a gas, which is 5/2, times 8.314 joules per mole, times the log of 373 over 298, and that's equal to 4.67 joules per mole Kelvin. And remember, this is a delta S, so this is the change. So if S for helium at 25 is 126 joules, we'll add the 4.67 and get that the S for helium at 100 degrees Celsius is about 131 joules per Kelvin. Likewise, if we decrease the temperature, we're going to decrease the entropy. And we can think about what would happen if we decrease the temperature all the way to 0. Well, if we decrease the temperature all the way to 0, there'd be no more motion of the particles. So the entropy would be all the way equal to 0, almost, but not quite. We'd also have to fix the arrangement of all of them. And what would that mean for 0 entropy? Well, this is the third law of thermodynamics, and this is just a definition that the entropy of a perfect crystal at 0 degrees Kelvin is equal to 0. So we can actually have something with no entropy, at least in theory. A perfect crystal is going to have perfect order, so everything will line up exactly. And at 0 degrees Kelvin, there'll be no movement of any sort of any of the particles in the crystal. So since they're all locked in place at a perfect arrangement, we would have no degrees of freedom, and hence the natural log of 1 is equal to 0, and the entropy would be equal to 0. A perfect crystal might look something like this, with everything lined up exactly if it was HCl with a positive negative. Whereas if there was some motion allowed, this would be imperfect, so there'd be a little bit of entropy at least. And the last thing we'll look at in this section is just calculating the delta G for a reaction overall. So given this reaction, delta G also follows the same principle as Hess's law. We can do products minus reactants. And so for this reaction, if we were given all the values, delta G for SO2, delta G for O2, the reactants, and delta G for SO3, and plug them all in, we'd get the overall delta G for the reaction.